Hello, I'm Hyesung Kwon. I'll present our work, Learning Self-Similarity in Space and Time as Generalized Motion for Video Action Recognition. This is a joint work with Manjin Kim, Swa Kwak, and Misu Cho at Postec. Video action recognition is the classification task, so the purpose of this task is to categorize videos by given a set of predefined target classes. As shown in examples, learning motion dynamics is crucial for video action recognition. Our work is motivated by the concept of self-similarity. In previous work, self-similarity is obtained by computing pairwise similarities between the query pixel and its neighbors. Since self-similarity suppresses variations in appearance and reveals geometric structures, it is often used as robust descriptors for matching or retrieval tasks. In this work, we bring the concept of self-similarity to the video domain. Self-similarity of video becomes three-dimensional spatial-temporal self-similarity. Since this self-similarity both includes similarities within a single frame and similarities between different frames, it not only reveals geometric structures, but also shows motion patterns. Here are examples of the spatial-temporal self-similarity called STSS. Left figure shows the STSS of the static object. Yellow STSS of the red query represents the geometric structure of the object. Right figure shows the STSS of the moving object. Green STSS of the purple query shows geometric structures and downside motion patterns. With a sufficient volume of neighborhood in space and time, STSS allows to take generalized motion information, including short-term and long-term, forward and backward motion. In this approach, we propose to learn the STSS representation in a fully convolutional manner and exploit to video action recognition. This page shows the framework of our method. We designed the STSS representation learning process as a neural block and name it a SELFY block. The block consists of three steps: self-similarity transformation, feature extraction, and feature integration. The input size and the output size are the same, and the SELFY block is inserted in the middle of neural architectures by element-wise addition for composing SELFY net. Now we will talk about each step in detail. In the first step, SELFY takes the input C-channel TXY video feature and generates a STSS tensor S. Cosine similarity is computed between the query and its neighbors for constructing the STSS. SELFY generates a L by U by V similarity volume per each position of the input, so the size of STSS tensor S becomes a 6D tensor that has TXY LUV dimension. Next step is feature extraction, which extracts STSS features from the STSS tensor. SELFY converts the similarity volume to L number of features by applying convolutions along LUV. These convolutions directly learn motion patterns as well as geometric structures from the similarities. Last step is feature integration, which generates the final STSS representation. Convolutions along TXY are applied for refining STSS features, and the features are fused to the STSS representation by 1 convolution. We now provide a comparison to the other methods. For the experiments, we adopt TSM ResNet 50 as a baseline and insert a single SELFY block to the baseline. We evaluate our SELFY net on standard motion-centric action benchmarks. In the tables, SELFY net obtains large accuracy gains compared to the baseline and sets a new state-of-the-art on all the benchmarks. We compare the proposed SELFY block with self-attention in fair conditions. Left shows the block diagrams of self-attention and SELFY, and the right table shows the action recognition performances. As shown in the table, SELFY substantially outperforms self-attention even with the small size of the kernel. The results validate that direct use of the STSS as motion representation is more effective in modeling temporal dynamics rather than using the STSS as attention weights. Thank you for your attention. Please see the paper and project page for more details.